Next up, we're going to look at the y86 instructions that manipulate the stack. I'm assuming that you're familiar with the stack data structure. What this is going to show you is how we actually implement a stack in hardware, and in particular, how the architecture itself supports the notion of a stack. The first thing that you have to wrap your head around is that when we talk about hardware, we almost always talk about stacks growing from the top of memory, or the largest address, down toward the smallest address. So if we think of this box as the whole address space of a processor, at the left, we have the low address, let's say 0, and at the right, we have the biggest address, let's say max adder. And our stack is going to grow from max adder down. And the reason for this is that it lets us put the code and data at the beginning of the address space and let it grow up. And now what you can do is let these two dynamic parts, the stack and the dynamic data, grow toward each other without having to a priori decide how big those regions are going to be. Let's look at this in a little more detail. So let's imagine that we've allocated the stack and we've got a bunch of space starting at hex address 1000 and going up to address 10A8. And you might say, wait a minute, why are you kind of pointing out in the middle of nowhere? And I ask you to be patient for a moment because it will become clear when we talk about how the push-Q instruction works on the y86. Push-Q is a 2-byte instruction. Its opcode is A. There's no function. And it only takes one register, which is RA, which is going to be the register whose contents we wish to place onto the stack. Or in other words, it's a register whose contents we're going to place into memory. Semantically, what this instruction means is it says, take what's in the stack pointer and subtract 8 from it. So in other words, the stack pointer is going to point to the last thing we put on the stack. And if we're about to put another thing on the stack, we're first going to move the stack pointer. So the first thing we do is we decrement the stack pointer, and now it's pointing to a location into which we want to place a value. So we've changed the address that is stored in the stack pointer from 10A8 to 10A0. Next, we're going to take the contents of the register referenced by RA, in this case, it's RAX, and we're going to take the value that's in that register, and we're going to put it into memory at the address to which the stack pointer is now referencing. So we're going to take this byte sequence, or that hex number, and put it into memory. How do we put it into memory? We put it into memory in little endian form. That means the least significant byte is 78, so that appears first, then the 56, then the 34, etc. So the quad value at address 0x10A0 occupies the bytes whose addresses are from 10A0 to 10A7. So that's what a push instruction does. Let's look at the inverse, which is the pop instruction. So now it's a 2-byte instruction. Its opcode is B, and it too takes a single register, RA. And what it's going to do is it's going to say, take the value in memory at the location of the stack pointer and put it into the register referenced by RA. So in this case, we've got several things on the stack already. The stack pointer is pointing to this location, whose address is 1088 hex. And the first thing we're going to do is we're going to take what's in memory at the address of the stack pointer. So this value here, which I hope everybody sees is just a 1. And we're going to place it into the register referenced by RA, which is RAX. So we take this value 1 and we put it in RAX. Then, just like we did with push-Q, we're going to have to adjust the stack pointer because we've removed something from the stack. And so now, instead of subtracting 8 from the stack pointer, we'll add 8 so that we can indicate that this location is sort of no longer on the stack. So what do I mean? We haven't done anything to the value that's stored in memory, but from the perspective of the stack, it's not there anymore because the stack pointer points to the next location. Okay. Let's look at how we might use the the push and pop instructions to implement a swap routine. Normally, you think of having an extra register in order to do a swap. And we're going to use the stack instead of an extra register. As soon as you start writing programs that use the stack, you have to remember to initialize the stack pointer. So that's what we're doing here. We're saying set the stack pointer up at hex 2000. Now, let's put some values in RAX and RBX. And now let's use the stack as our temporary store to do a swap. So we're going to take the value that's in RAX and we're going to push queue it, which means we've saved it into memory. Now we can clobber RAX by taking what's in RBX and putting it there. And what we can do is then restore the value that we put on the stack into RBX, thus having swapped those two values by using the stack as temporary storage. Ideally, after you write some more y86 programs and read some more programs, use of the stack will be completely intuitive.